On a screen in Munich, a claim about quantum matter sits colored red, still unproven. A proof-checking program runs, and line by line, the argument turns green, every logical step confirmed. The unusual part is who wrote that proof. Not a person, but a small team of AI agents working together, with humans only checking in now and then. Here is what got proved. It is a result called the fundamental theorem of matrix product states, and it answers a very specific question. When do two different-looking descriptions of the same quantum system actually describe the same physical state? The paper came out of Ignacio Cirac's group at the Max Planck Institute of Quantum Optics in Munich, from Sirui Lu, Erickson Choa, and Cirac, and it went online in early July 2026. To see why that question is hard, you need to know what a matrix product state is. Picture a row of quantum particles in a line, like atoms in a chain. Writing down the full quantum state of that chain, the naive way, is hopeless, because the number of amplitudes explodes as you add particles. A matrix product state is a compact trick. Instead of one enormous table of numbers, you store a small matrix at each site, and you get any amplitude by multiplying those matrices along the chain. The picture physicists draw is a line of little boxes, one per site, with legs connecting them. The catch is that this description is not unique. You can slip an invertible matrix onto the bond between two sites and cancel it with its inverse on the other side, and every physical prediction stays exactly the same. So two tensor chains can look completely different on paper and still be the same state. The fundamental theorem pins down the rule. Once you put the tensors into a standard canonical form, two of them generate the same family of states for every chain length precisely when they are related by one of these invertible changes on the hidden bond indices. It tells you which different-looking diagrams are secretly identical. Now, the part that makes this a story about machines. The proof was written in Lean 4, a proof assistant. In a proof assistant, every single step has to pass a small, trusted checker called the kernel. You cannot wave your hands, skip a lemma, or say, it's obvious. If a step does not follow from what came before, it simply does not compile. When the authors report that the core chain of this theorem has no unfinished gaps left in it, that is a strong claim. There is no place in the argument where someone wrote a placeholder and moved on. The computer confirmed the whole path. So how did the agents actually do it? This was not one giant model asked to spit out a proof. It was a team with jobs. An orchestrator broke the work into tasks and handed them out. One agent scouted Lean's existing math library for tools it could reuse. Another wrote the actual proofs. Another cleaned them up. Another kept a shared written document, a blueprint, in sync with the code. And a reviewer compared three things at once: the original physics papers, the blueprint, and the Lean code, flagging any place they drifted apart. When a proof failed or a mismatch showed up, the work bounced back for repair. Between sessions, the agents kept a persistent memory of corrected conventions and dead ends they had already ruled out. Something surprising happened early on. The team asked the system to prove the theorem without pointing it at any particular reference. For one important case, the agents reached for a classical result from abstract algebra, the Skolem-Noether theorem, and built the proof around it. That route is not the standard one physicists use for this problem. The agents chose it on their own, apparently because Lean's library already had the algebra machinery to make it work. A search for the easiest available path led to a proof that was a little off the beaten track. To pull this off, the agents had to build things that did not exist yet. Lean's standard library did not contain large parts of the quantum information math this proof needs, so the project created them. The theory of quantum channels, a quantum version of the Perron-Frobenius theorem, and more, filling 5 specific gaps where the standard library came up short. The result is a public library the team calls TNLean, tens of thousands of lines of verified code, released alongside a human-readable blueprint that runs about 150 pages and links every theorem to its formal counterpart. They even pushed the formal machinery toward a real physics payoff, classifying certain phases of one-dimensional quantum matter, the symmetry-protected topological phases, by turning a symmetry of the state into a fingerprint you can read straight off the bond structure.
But the headline finding is not that AI can grind out proofs. It is where the whole thing nearly breaks. A proof assistant checks that your theorem follows from your assumptions. It does not check that your theorem is the one you meant. And the agents kept quietly proving the wrong statement, a version that was a little too narrow, or that secretly assumed the very thing it was supposed to establish. Each of those proofs was completely valid to the machine. They were just answers to a slightly different question. The authors put it bluntly, echoing a line from the field: definitions are more dangerous than proofs.
That is why the humans and the blueprint were not decorations. The blueprint was where the intended meaning lived, in ordinary mathematical language, so a human reviewer could confirm the statement said the right thing before the kernel ever confirmed the proof was correct. Enforcing that faithful match at the scale of a research-level theorem was the real bottleneck the team ran into. It is also why this is honest, expensive engineering rather than free autonomous science. The whole effort ran on a mix of commercial AI models over about 5 months and cost roughly $20,000 in model usage, with people setting the direction the entire way.
So what actually changed here? For the first time, a coordinated team of AI agents carried a research-level theorem in mathematical physics all the way to a machine-checked proof, invented new formal libraries to get there, and even found an argument the textbooks do not use, while a proof assistant guaranteed that not one step was taken on faith. The limit is just as clear. The machine can certify that the logic is airtight, but it still takes a human to make sure the airtight logic is about the right thing. That boundary between what a proof checks and what a person still has to mean is the frontier this work maps out.